A high-speed train traveling at over 300 kilometers per hour is not merely a vehicle, but an intricate symphony of advanced metallurgy, aerodynamics, and electromagnetism. Building a machine capable of safely sustaining such immense velocities begins with the construction of the car body, which must be astonishingly light yet rigid enough to withstand intense aerodynamic pressures. The manufacturing process does not use heavy steel framing like traditional passenger trains. Instead, the raw material consists of massive, hollow extrusions of aerospace-grade aluminum alloys. Giant hydraulic presses force heated, softened aluminum billets through steel dies, creating long panels with an internal double skin structure. This double skin is essentially two flat outer surfaces connected by diagonal internal trusses, forming a honeycomb-like cross-section that provides immense structural stiffness while eliminating thousands of pounds of dead weight. To assemble these long aluminum extrusions into the floor, walls, and roof of a train car, manufacturers employ a highly specialized technique called friction stir welding. Traditional arc welding melts the metal, which can cause warping, alter the metallurgical properties of the aluminum, and introduce microscopic pores. Friction stir welding avoids melting entirely. A spinning, incredibly hard cylindrical tool is plunged into the seam between two closely fitted aluminum panels. As the tool rotates at high speed and travels along the joint, the immense friction heats the aluminum until it becomes a soft, pliable plastic state. The spinning tool physically churns and mixes the metal from both panels together, forging a continuous, seamless bond as it cools. The resulting weld is flush, perfectly smooth, and often stronger than the surrounding metal. Once the primary shell of the train car is welded together, it is moved into a colossal computer numerical controlled, or CNC, gantry milling machine. This gigantic robotic milling center spans the entire length of the train car. Equipped with spinning carbide router bits and flooded with cutting fluid, the CNC machine carves out the exact openings for the doors, windows, and roof-mounted equipment. The tolerances here are kept within fractions of a millimeter, ensuring that when the glass and doors are eventually installed, they fit perfectly flush with the exterior skin. Any protrusion, no matter how small, would generate turbulent air, creating immense aerodynamic drag and unwanted noise at high speeds. While the main passenger cars are built from extruded aluminum, the aerodynamic nose of the leading car demands a completely different approach. The complex, sweeping, three-dimensional curves of the train's nose cannot be efficiently extruded or welded. Instead, it is manufactured using advanced composite materials, primarily carbon fiber reinforced polymers. Inside a cleanroom environment, technicians manually lay up hundreds of individual sheets of woven carbon fiber over a meticulously shaped mold. Each layer is pre-impregnated with a precise amount of epoxy resin. The orientation of the carbon fiber threads is carefully staggered layer by layer to provide multi-directional strength, particularly against bird strikes at 300 kilometers per hour. Once the layup is complete, the entire mold is sealed inside a vacuum bag to extract all trapped air, and then rolled into an autoclave. The autoclave is a massive industrial oven that applies extreme atmospheric pressure and high heat, curing the resin and permanently binding the carbon fibers into a single, rigid, ultra-lightweight nose cone. As the shell takes shape above, the critical foundation of the train is forged below. The undercarriage units, known as bogies, house the wheels, axles, suspension, and motors. Creating a high-speed railway wheel is a brutal metallurgical process. Traditional casting, where molten metal is poured into a mold, is unacceptable because it can leave microscopic internal voids that would violently shatter under the stress of high-speed travel. Instead, wheels are forged. A solid billet of high-carbon steel is heated in a furnace to over 1200 degrees Celsius until it glows a brilliant translucent orange. A hydraulic press exerting over 10,000 tons of force crushes the glowing billet into a rough wheel shape, aligning the internal grain structure of the steel for maximum strength. The rough wheel is then transferred to heavy-duty CNC lathes, which carefully peel away ribbons of steel to machine the wheel to its precise final dimensions. The profile of a high-speed train wheel is one of the most critical engineering details on the entire machine. Because the wheels on opposite sides of the train are permanently fixed to a solid steel axle and must rotate at the exact same speed, navigating a curve presents a serious geometric problem. The outer rail of a curve is physically longer than the inner rail. To compensate for this without allowing the wheels to slip or drag, the steel wheels are machined with a subtle conical profile, meaning the tread is not a perfect cylinder. The part of the wheel closest to the train body has a slightly larger diameter than the outer edge. As the train enters a curve, the centrifugal force gently pushes the train outward. This outward shift causes the larger diameter of the outer wheel to ride on the rail, while the smaller diameter of the inner wheel rides on the inside rail. The outer wheel is now effectively larger and travels further per revolution than the inner wheel, allowing the solid steel axle to steer itself naturally around the curve, without any moving steering components. Attaching the wheels to the heavy steel axle requires a process called shrink fitting. The axle is machined to a diameter that is just fractions of a millimeter larger than the center hole of the wheel. The wheel is then heated using powerful electromagnetic induction coils, causing the steel to thermally expand and the center hole to widen. The cold axle is seamlessly slipped into the expanded hole. As the wheel cools to room temperature, the steel shrinks back to its original size, clamping down on the axle with an unimaginable, permanent grip that requires no bolts or welds. The solid wheel set is then mounted into the bogie frame. The frame itself is welded together from thick plates of high tensile steel. Because the bogie bears the entire dynamic weight of the train, every single weld on the frame is inspected using ultrasonic testing and X-ray radiography to detect any internal flaws or hairline fractures. The suspension system that connects the wheel sets to the bogie frame and the bogie frame to the train car is extraordinarily complex. It is divided into primary and secondary stages. The primary suspension consists of heavy steel coil springs and dense rubber bushings situated right above the axle bearings. This stage absorbs the harsh, high-frequency impacts directly from the steel rails. The secondary suspension sits between the bogie frame and the passenger car body. Unlike the steel coils, the secondary suspension utilizes massive pneumatic air springs. Onboard compressors inflate thick rubber bellows with pressurized air. This not only provides a cloud-like ride for the passengers, effectively isolating them from the heavy machinery below, but also functions as an active leveling system. Electronic sensors monitor the height of the train car. When a large crowd of passengers steps onto the train, adding thousands of pounds of weight, pneumatic valves instantly inject more air into the springs to prevent the train from sagging, keeping the floor perfectly level with the station platform. The suspension must also counteract a terrifying physical phenomenon known as hunting oscillation. Because of the conical shape of the wheels, naturally seeking the center of the track, a train moving at very high speeds has a tendency to sway violently from side to side in a sine wave pattern. Left unchecked, hunting oscillation will literally tear a train off the tracks. To prevent this, massive hydraulic cylinders called active yaw dampers are installed longitudinally between the bogie and the car body. These dampers are filled with viscous oil and controlled by computers that read lateral acceleration hundreds of times a second. Whenever the bogie begins to sway, the yaw dampers instantly stiffen, locking the bogie into a perfectly straight line, while still allowing it to pivot gently when an actual curve in the track approaches. Supplying the massive amount of energy required to propel this heavy assembly through the atmosphere begins on the roof of the train. Powering a machine that draws up to 10 megawatts of electrical energy while traveling at 85 meters per second requires maintaining flawless physical contact with an overhead high-voltage wire. This is achieved using a pantograph, a folding, articulated arm mounted on the roof. The topmost part of the pantograph, known as the contact shoe, is fitted with a replaceable strip of pure graphite. Graphite is chosen because it conducts electricity efficiently while acting as a dry lubricant, preventing excessive mechanical wear on the stationary overhead copper wire. However, aerodynamic drag pushes the pantograph violently upward at high speeds, while the physical wire sags slightly between its support poles. To maintain a constant steady pressure against the wire without snapping it, the pantograph utilizes an active pneumatic suspension. Regulated air cylinders continuously adjust the upward force, compensating for the fluctuating height of the wire and the extreme aerodynamic forces. Interestingly, the overhead wire is not suspended in a perfectly straight line down the track. It is intentionally staggered in a subtle zigzag pattern. As the train moves forward, the wire sweeps left and right across the graphite contact strip, ensuring the friction wears the graphite evenly across its surface, rather than slicing a deep, dangerous groove into the middle of the shoe. Once the 25,000 volts of alternating current enter the train through the pantograph, they travel down into massive, heavy transformers bolted underneath the floor of the train. Because these transformers generate immense heat, they are sealed in heavy metal tanks filled with highly refined dielectric mineral oil, which circulates through forced air radiators to shed heat into the passing slipstream. The transformer steps the terrifyingly high voltage down to a manageable level. This lower voltage alternating current is then fed into a silicon rectifier, a bank of specialized diodes that force the electricity to flow in only one direction, converting the alternating current into a flat, steady direct current. This direct current flows into the heart of the train's brain, the traction inverter. The inverter utilizes solid-state electronic switches called insulated gate bipolar transistors, or IGBTs. These advanced transistors have no moving parts and can turn immense amounts of electrical current on and off thousands of times per second. By rapidly chopping up the direct current, the IGBTs utilize pulse width modulation to synthesize a completely new alternating current. The onboard computers can manipulate these electronic pulses to perfectly control both the voltage and the precise frequency of this new alternating current, which is then sent directly to the traction motors. The traction motors themselves are a triumph of physics, specifically utilizing a three-phase asynchronous alternating current design. Mounted tightly within the steel bogie frames, these motors contain no electrical brushes and no physical contacts between the stationary outer housing and the spinning inner shaft, making them nearly immune to wear. The stationary part of the motor, the stator, is lined with heavy copper coils. When the synthesized alternating current from the inverter surges through these coils, it generates an invisible, incredibly powerful magnetic field that rotates rapidly around the inside of the motor. The spinning inner shaft, or rotor, is constructed of stacked iron plates embedded with thick copper bars. As the stator's invisible magnetic field sweeps past the stationary copper bars of the rotor, it physically induces a powerful electric current inside the rotor itself. This new current instantly generates its own counter-magnetic field. The magnetic field of the rotor furiously attempts to chase the rotating magnetic field of the stator. The magnetic repulsion and attraction between the two fields create immense rotational torque, forcefully spinning the rotor, which is connected via heavy-duty steel reduction gears directly to the axles, driving the steel wheels into the rails. When a train traveling at high speed needs to stop, relying solely on mechanical friction would quickly melt standard brake pads and discs. Therefore, high-speed trains employ a three-tiered braking system, the primary of which is regenerative braking. When the driver commands the train to slow down, the traction inverters dynamically alter the frequency of the electricity sent to the motors. The invisible rotating magnetic field in the stator is instructed to spin slower than the physical rotor. Instantly, the physics of the motor reverse. The forward momentum of the heavy train physically forces the rotor through the slower magnetic field, turning the traction motors into massive electrical generators. The kinetic energy of the speeding train is violently converted back into raw electricity. This creates immense magnetic drag on the axles, smoothly slowing the train. The freshly generated electricity flows back through the inverters, up through the pantograph, and is returned directly into the overhead power grid for other trains to consume. For even more stopping power, eddy current brakes are utilized. Long electromagnets are suspended from the bogie frames just millimeters above the steel rails. When activated, direct current flows through these magnets, generating powerful localized magnetic fields that penetrate the steel rail below. According to Lenz's law, the forward motion of these magnetic fields induces swirling electric currents, known as eddy currents, directly inside the solid steel rail. These eddy currents produce their own magnetic fields that perfectly oppose the direction of travel, creating a massive dragging force that pulls backwards on the train without any physical part ever touching the rail. Only at lower speeds, or in an emergency, do the mechanical friction brakes engage. Massive alloy steel ventilated discs are bolted directly to the axles and the inside faces of the wheels. Pneumatic cylinders violently clamp heavy calipers around these discs. The brake pads are not made of standard automotive materials, but of sintered metals, a blend of iron, copper, and carbon powders fused together under extreme heat and pressure, capable of surviving temperatures exceeding 800 degrees Celsius. A computerized wheel slip protection system, similar to anti-lock brakes on a car, monitors the precise rotational speed of every single wheel. If one wheel begins to lock up and slide on the steel rail, the computer rapidly pulses the pneumatic pressure to that specific caliper, preventing the wheel from skidding and grinding a dangerous flat spot into the perfectly round steel tread. Managing the aerodynamic physics at 300 kilometers per hour dictates every aspect of the final assembly. As the finished bogies are mated to the aluminum car bodies, the enormous spaces between the train cars are shrouded in heavy, flexible rubber diaphragms, ensuring the exterior of the entire train acts as one continuous, smooth aerodynamic surface to reduce skin friction. The doors plug flush into the body, and the windows are permanently sealed. The entire train is pressure sealed like the cabin of a commercial airliner. This is not for high altitudes, but to protect the passengers from extreme barometric pressure changes. When a high-speed train plunges into a long tunnel, it acts like a piston in a cylinder, violently compressing the air in front of it. This creates a high-pressure shock wave that travels down the tunnel at the speed of sound. Without heavy pressure sealing and massive active ventilation valves that snap shut the millisecond the train enters a tunnel, the sudden barometric spike would instantly burst the eardrums of everyone on board. As the train travels through the tunnel, that compressed wall of air reaches the exit portal and explodes outward as a micro-pressure wave, creating a deafening sonic boom that can shatter the windows of nearby houses. This is precisely why the carbon fiber nose cones of high-speed trains are so incredibly elongated and shaped like the beak of a kingfisher bird. The sweeping aerodynamic profile does not punch a blunt hole into the air, but rather acts as a gradual wedge. It slowly and smoothly parts the air over a long distance, significantly reducing the intensity of the micro-pressure wave and eliminating the tunnel boom effect entirely. All of these thousands of systems, from the friction stir-welded aluminum and the precision-machined conical wheels, to the gigahertz switching inverters and the invisible magnetic forces of the asynchronous motors, are perfectly synchronized by rows of redundant onboard computers. These computers continuously talk to digital transponders bolted directly to the railway ties, receiving real-time data about track curvature, speed limits, and the exact distance to the train ahead. The seamless marriage of heavy industrial metallurgy, microscopic solid-state electronics, and aggressive fluid dynamics results in a machine that permanently redefines our mastery of distance, floating tirelessly over continuous welded steel rails and constantly pushing the boundaries of physical engineering.